Example 3. A sample of bacteria contained 387 cells. 24 hours later, the sample was recounted and was found to have 8,012 cells. Determine the doubling period of the bacteria to the nearest tenth of an hour. Alright, again, we're going to start with our formula. Y equals A times B to the power of T over P. So in this case, we know that at the very end it had 8,012 cells, so that's going to be our Y value, or our final value. A is our initial value, so 387. Now our rate of change, well, we're talking about doubling, and that's found in the words here, so that means we're going to have a 2 as our base. And now this time frame. So it looks like we were found over 24 hours. So T is going to be 24. And that looks an awful lot like a 29, so let's fix that up. And then P is actually what we're looking for. What is the period it takes to double? So I'm going to divide both sides by 387, and I get 20.70 equals 2 to the power of 24 over P. Again, logarithm would be really helpful here. So we're going to just graph this, and we're going to get P equals to 5.5 hours. Which means that our doubling period of the bacteria is 5.5 hours. Let's take a look at a lot trickier question. So Barbara invested $8,000 in an account which pays interest at a rate of 6% compounded semi-annually. How much money will Barbara have after 5 years? Now, if you just read this quickly, you might not notice some of the issues. The semi-annually, you might not know what that means yet. And compounded, maybe you don't know. So let's just start off with our formula. So that's Y equals A times B to the power of T over P. There is actually a compound formula, but it's not worth it. You're not given it on the diploma or a test. So you might as well learn how to actually derive the proper thing from this formula. And it's not too bad. So first of all, Y. Well, that's what we're looking for. We want to know how much money. So we'll just leave that as Y. A is our initial amount, and that's $8,000. B is our rate of change. Now this is where it gets tricky. Okay, it might be very tempting to say, hey, it's 6%, so therefore it's 0.06, and it's actually 1.06 because we want that total as well. And that might be true if this was compounded annually, meaning the interest was given every once a year. But semi-annually means twice a year. And so how banks do that then is they split that 6% up over how many times it happens in the year. So in this case, it happens twice. So we actually have an interest rate of 3% every 6 months that happens, which is 0.03, but we need that initial amount, so it's 1.03. So our rate of change is 1.03. And also this exponent is a little bit tricky as well. So T in our case is 5 years. We're told we're doing this for 5 years. And it's the time period that's a little bit tricky. And maybe if we put the units here, it'll be more obvious. This is 5 years. But our period is actually 0.5 years because this is semi-annually, or every 6 months, which is also 0.5 years. So when I actually simplify this, this actually simplifies out to 10. And if you use the compound interest formula, you would find that this is 10 as well. But again, you're going to run into questions where maybe that interest formula doesn't work and that this is going to be your best friend. All that can go into the calculator all at once. You get 10,751. It's money, so we should round to the second decimal place or the hundredth. And we're in dollars. All right, B, how long will it take for her investment to triple? So I want 3 times 8,000. That's her initial investment. And I have 8,000 here as her initial investment. And we know it's 1.03. And this time we're looking for T. So we still know that this is 0.5. And so I'm going to divide both sides by 8,000. So I get out the equation 3 equals, so there should be a 0 here, 1.03 over t over 0.5. Now I'm going to need to do that into my calculator, and I'm going to find out that t is actually equal to 19 years. On to C then. So if Barbara is investigating other investment opportunities, at what annual rate to the nearest tenth must she invest her money so that it doubles every 7 years? So we'll use our formula we already made. We want double her investments. We'll say 2 times 8,000 is still her initial investment. So A is still 8,000. We're not sure what the rate of change is, so we'll leave that as B. And the tricky part is this T over P part. So it's over 7 years. Now this period, again, because it's semi-annually, it's going to be 0.5, which really equates to 14. So I'm going to be b to the power of 14. Now when I'm solving this, so I'm going to divide both sides by 8,000. So I get 2 equals b to the power of 14. And then I'm going to go b. So the opposite of to the power of 14 is taking the root 14 equals b. And so in our calculator, you're going to find out that that's equal to 1.05. Now we have to be careful for a couple of reasons. First of all, this one part here, that's from our initial amount. So right now it looks like the interest rate is actually 0.5 as a decimal, or 5%. But that's actually not true. That's only every 6 months you're getting 5%, which really means that it's actually 2 times 5% for that full year, which is normally what interest rates are done in. So we actually need a 10% increase every year to double every 7 years. And there's a rule of 72 that says that if you take your interest rate and you divide that by 72, or 72 divided by the interest rate, that'll tell you how many years it takes to double. So that's what 7.2. You can see our answer is reasonable then, that it would be 10% interest rate. Just be careful with that though, it's more of an estimation than anything. Our final example. So we have this information more, but we've been using the whole time. We are going to use y equals a times b to the power of t over p. So a sample of saliva was taken from a patient, and it was determined that 387 cells of bacteria were present. If this strain of bacteria doubles every 5 hours, so we got a couple things. Determine the number of cells that will be present after 24 hours. So again, using this equation, we're looking for the total number of new cells. So that's going to be a y equals then. A is our initial amount, so 387, times our rate of change. Now we're looking for doubling, so that means the rate of change will be 2. And t is our time period. So in this case, our time period appears to be 24 hours based on the question. And then over how long the doubling period is, which is 5 hours. And all of that can be put into your calculator all at once, and you're going to find that there's 10,781 cells. B, determine the length of time it will take for the sample to grow to 5,000 cells. Okay, so 5,000 is our final amount. That's where our y variable is. Our initial amount seems like it's the same according to the question. We're still looking for a doubling. This time, though, we're looking for t. We're looking for that time. We still know that it doubles every 5 hours. So that's where that 5 is going to be represented. So we're going to divide both sides by 387. I'm going to get 12.91898 ... is 2 to the power of t over 5. Now, I could use a calculator right here. I could also do a little bit more work by hand. I'm going to use flower power to simplify the right side. So this is going to be a power of t and a fifth root. So actually, I can take both of these and raise them both to the power of 5, because the opposite of fifth rooting. So that will cancel out. Now we're going to get a really large number, which is kind of the bad thing about doing this. And on your graphing calculator, it's going to be a little bit annoying searching for where that intersection point actually is. Wasn't much better on Desmos. But you get that's equal to 2 to the power of t. So we're really looking for those logarithm laws so that we don't have to keep on using a graphing calculator. we do find that t is equal to 18.5 hours.